Yes, thank you. Okay, molecular formula. So I'm going to give you an example. All right, simple example. H2O2. Use it to bleach hair. It's peroxide. Okay, hydrogen peroxide. The molecular formula is that. Okay, now the empirical formula is the simple ratio of that. It's actually HO. All right. Okay, so the molecular formula is exactly what is inside the molecule. Okay, all of the atoms. Okay, the exact number of atoms of each element present in the formula of the compound. The empirical formula, however, is something that's slightly different. It's like the simplest whole number ratio of atoms of each element in the compound. Okay, now we can use both of those and our knowledge of moles in order to work out what the true molecular formula is of a substance, if we get to know the amount of, if we get to know molecular masses and also have knowledge of the empirical formula. Something went wrong. So I'm struggling to get in, so something went wrong. Okay, what you'll need to do is you reset and then come back in, but don't worry, it's all recorded. Okay, so here's an example, right? A compound that contains 10 grams of hydrogen. Now, immediately you can look at that and you can think, right, 10 grams of hydrogen, all right, how many moles of hydrogen is that? Bearing in mind the relative atomic mass of, yes, that's fine, Rue. Relative atomic mass of hydrogen is 1. How many moles is 10 grams? Okay, so all you would need to do is then think, right, okay, 1 goes into 10 times, so I have 10 moles. The formal way of calculating that is mass in grams divided by relative atomic mass, because we already have learned this equation, yeah, number of moles, yeah, number of moles equals mass, so your sample mass. Okay, this is what we did all throughout last week over the relative formula mass. So if it's for an element, it's going to be AR. If it's for a molecule, it's going to be the relative molecular mass MR. Okay, so we learned that last week. So using that twice over, you can actually work out the number of moles in this question. 10 grams of hydrogen contains 10 moles. 80 grams of oxygen contains 5 moles. So you're talking about a sample of a compound, right? That has 10 moles of hydrogen, 5 moles of oxygen. All right. It is H2O, so that does make sense, because you would expect to have 10 moles of hydrogen atoms. Should say. Okay, I should mention. Should have 10 moles. If you started off with, where's my pen? If you started off with, or if you were told that you had 5 moles of atoms, it's a 2-to-1 ratio. Okay, it's a 2-to-1 ratio. All right. All right. So in a molecule, you can see that. You can see it in the simple one. This is a 2-to-1 ratio. All right. If you had a collection of the molecules, you would also have a 2-to-1 ratio as well of hydrogen to oxygen. Are there any questions? Okay, so to conclude with that point, let me just scale this in to since you have equal numbers of moles of atoms, right? So it's equal number of moles of atoms contain the same number of atoms. The ratio of hydrogen atoms to oxygen atoms is 2-to-1. Hence, the empirical formula is H2O. Right? Now, try not to think about H2O. Right? Try not to think about H2O. If you actually just had information that said this is a compound of hydrogen and oxygen, and it contains 10 moles of hydrogen and 5 moles of oxygen, what's the simplest ratio that you have? The answer is 2-to-1. So your empirical formula is H2O, because that's the simplest whole number ratio of atoms of each element in that compound. Any questions?
No, sir.
Right. Okay, right. So I'm going to give you some examples of the relationship that there is between empirical and molecular formula in the next slide, which is slide 3. I'll give you a better version of this very shortly. A version of the table, because it's a little bit blurry. Okay, of course, you'll have it in your PowerPoint as well. I'm just going to blow up this table just for a moment. Okay, so you can see it, especially if you've got problems and issues with your devices. Okay, so methane, right? The empirical formula, CH4, that's just like methane, which is this molecule here. Okay, so let me just draw some methane. Okay, C, single bond, single covalent bonds, that's methane. Okay, all right. So you can see that's CH4. All right. You would say that the molecular formula is CH4, and that is also the simplest ratio of carbons to hydrogen. Okay, so that works out. Now we're going to go to ethane. Okay, so ethane, it's slightly different. Okay, ethane is this. My writing is too fast for the computer. There we go. I'll try to write slowly a bit. Computer can't handle it. There we go. So that's ethane. All right. So the molecular formula for ethane is C2H6, right? Nothing revolutionary. Nothing revolutionary there. Hamid, leave my box alone. Okay. But the simplest whole number ratio is actually CH3. That's your empirical formula. Okay. This is your molecular formula. Okay. All right. So you can actually see that there is actually a factor of 2 between the two. So to go this way, you have to multiply everything by 2. Okay. You have to multiply that 1 by 2. You have to multiply that 3 by 2, and then you get 2 and you get 6. Is everyone okay with that?
Yes, sir.
All right, okay. Now that's actually a very important step. There's a reason behind me actually explaining that, because if we get told what the empirical formula is, and then we get told what like this, the relative molecular mass of this is 1224. This is 30. Okay, all right. So if we get told the empirical formula is that, and we get told that the relative molecular mass of whatever our target molecule is 30, and we don't get told that, we can actually figure that out. Because if we actually have a mass over here, which is 15, this is an empirical formula which is 15, right? So the relative molecular mass, the molar mass of your empirical formula is 15, and we then realize that to get from 15 to 30, you have to multiply it by 2. Each of these numbers then has to be multiplied by 2, and then you'll actually get your molecular formula. Are you following me? Yeah.
Yes, sir.
Yes,
All
sir.
right. You can see where these questions are going to be going. Yeah. So that's how they design their questions. All right. They're going to give you empirical formula. They're going to say what the molecular mass is, and then they're going to ask you to figure out what the molecular formula is of the target molecule. Okay, that's how they design their questions. I'm going to give you an example that we're going to work through on slide 4. Okay, so move to slide 4. So this is a typical past paper question that they can that has come up, like, you know, kind of changed it around a little bit, but that's fine. So the empirical formula of X is, right? So this is the empirical formula. Remember that the empirical formula is the simplest whole number ratio, okay? Simplest ratio. So we could have some possibilities. We could have C4H10S1. We could have X as being C8H20S2. We could have it C12H30S3. Okay, so each time we're actually multiplying it by the next number up. So that's multiplied by 2, or this one would actually be multiplied by 3. So the only information that we've actually got now is that the relative formula mass of X is 180. So now we have to try and figure out which one of these has like a relative formula mass of 180. All right, We get given that information, we get given that info, and get given that info in the periodic table. All right. So that looks like a lot of number crunching. Yeah. Ahmed, you said no, sir. What's up? Which bit? Are you right?
Oh, no, that was old.
Oh, all right. Okay. Are you okay?
Yes, sir.
All right.
Okay.
I can go back. I can go back. You can pull me back anytime, right? Okay. Right. So we got a situation. All right. Now, what we could do is we could sort of like think, all right, well, what's the mass of that? What's the mass of that? Let's just keep going until we get to one, which is 180. Okay. Yeah. That would seem like a straightforward way of figuring it out, and whatever it is, then we've actually got the molecular formula of X. So it will either be that or that. The problem is that this can actually go on and on and on forever. Okay, so what we could do is we could take a slightly more calculated approach. Okay, so move on to the next slide. All right. So this is part of the working out that you would have to do. So we are now on slide 5, all right? And now what we're going to do is we're going to finish this, all right? So step 1, what you have to do for each and every single question that is like this, you have to calculate the relative formula mass of the empirical formula. So start off with that, okay? That's your step 1, okay? The working out is here, but it's 12 times 4 plus 10 times 1 plus 32, okay? That's basically what you can do. And right, when you're really, really cool at this, you can actually do that in your head. If you're not, don't worry, just do it in the calculator. So the relative formula mass of that is 90. Now, at that stage, it's worth taking a step back because you think, oh, 180, isn't that just multiplied by 2? Yeah? So if that is multiplied by 2, then all you need to do is just double all of these. Yeah? And you get your answer, because that then gives you your molecular formula of X. And then you can double check it. So what we could do is we could double check it, right? Let's say, for example, we've made that step. Let's double check the formula mass of this molecule. So what is 8 times 12? What's 8 times 12?
96.
96, right? What's 20 times 1?
20.
Come on, we got some top setters here. 20 times 1, that's not beyond you. And 2 times 32.
64.
All right, add those up, see what you get.
$180.
180, all right? So if 180 is your answer, we've got it, all right? The formula mass of that is 180. So therefore, your molecular formula is that. Okay? Any questions?
No, sir.
All right, okay. Let's move on. We're almost there. We've got 2 more types of calculations that they will ask you. Okay, this is a popular one because it actually throws people. Calculating percentage yield and percentage purity of the product. So let me see. I'll show you an example of the type of question that they can actually ask for this one. Now, this is a question that is gonna trap a lot of you, even though you're good. All right, it's gonna even if you're good, it's gonna trap you, because what you're gonna be able to do is you're gonna be able to you're gonna unfortunately put yourself in a situation where you're putting the wrong numbers in the right places. So have a bit of patience with this and try and understand what this is all about. Basically, when you have experiments, I'm going to delete the example, otherwise it's going to be distracting for you. In slide 6, that's where we all are. If you have an experiment, right? And let's say, for example, you react this solid, yeah, right, with this solid, all right, okay. You react 2 solids together. You that looks like a funny face. You automatically think, oh right, okay, everything is going to react, right? Everything is going to react. All right, everything is going to react, and nothing is imperfect. Everything happens. All right. Okay, the reality of the situation is you kind of get like you probably get that much actually, yeah, and what you're left over with is a hang on a second, pen's running out, is a small, why isn't this working? Oh, that's because it's white. A small amount of that and a small amount of that left over. Okay, percentage yield. So the reality of the situation is you're kind of like left with that. Okay, you're kind of left with that. So take a step back, go back to Wonderland. Yeah, so we're Alice in Wonderland, right? If Alice in Wonderland did this experiment, everything would work. Okay, all right, that's your theoretical yield. All right, that's your Alice in Wonderland, where everything is working. Okay, all right, the reality of the situation when you're in a lab is that you are not in Wonderland. Okay, and you're left with quite a bit. So over here, this amount over here is the actual yield obtained. Okay, actual yield obtained. Okay, so this calculation, actually, percentage yields give you an idea of how badly your experiment has failed in making desirable product. Yeah. Okay, if you have a high percentage yield, that means that you're quite successful. If you got a low percentage yield, that means that you're not a very good chemist, and you need to try and figure out, well, you are a good chemist, but you need to try and figure out like a different way of making what it is that you want to make. Okay, all right, so I'm going to ask you to go into the next slide. I'm going to have a look at this calculation. All right, so this is a past paper question. Okay, this past paper question, don't worry about the chemicals that are there. All right, I'll take you through this. Okay, don't worry about the different chemicals and the chemical reactions actually taking place. All right, basically what's happening is this, right? You've got displacing copper from copper sulfate. It's just a displacement reaction. You start off with 6.5 grams of zinc. Okay, you add it to an excess of copper sulfate, copper 2 sulfate. Copper was filtered off. Okay, so you're actually going to make a certain amount of copper. Okay, the copper was filtered off, washed and dried. The mass of the copper obtained was 4.8 grams. Immediately, your chemist's brain should start to be thinking, how many moles of each have I actually got? Okay, all right. Now, there are two possible ways, like two different ways that you can get yield. One is Alice in Wonderland, right? And one is what we're actually getting in this experiment. Okay, so the Alice in Wonderland version, I'm actually going to show in green. Okay, but let's figure out how many moles there are. You've got a mass, all right? So your amount in moles from last week, okay, equals mass, which is 6.5 over the relative atomic mass of zinc, which happens to be 65. Oh, look, it's really convenient. Okay, so what we've actually got is 0.1 moles of zinc. We start off with that. Okay, now in this equation, in the equation of the reaction, right? So there could ask you a question about that, but I'm aiding you. Okay, this reaction takes place. All right, now you only need to look at certain parts of this reaction. Okay, the only thing that you need to look at is here, and that doesn't help. The only parts that you need to look at are here and here. Okay, so this is telling me that one atom of zinc will form one atom of copper. What do you think 1 mole of zinc will form theoretically in Wonderland? How many moles of copper will that form? If 1 atom of zinc forms 1 atom of copper, what would 1 mole of zinc form of copper? Come on, folks. Folks, I need a response. What's going on? If 1 atom of zinc forms 1 atom of copper, what does 1 mole of atoms of zinc form of copper?
1 mole.
1 mole. How can it form 0.1 moles? Oh, you're looking ahead, aren't you? You're looking ahead, Ahmed. So you're right. 1 mole of zinc, 1 mole of zinc would form 1 mole of copper. So in Wonderland, Ahmed, 0.1 mole of zinc would form 0.1 mole of copper. Tell me that you're okay with that. Okay, that's in Wonderland. That's if we've not lost anything. That's if you've got your yield obtained over the theoretical yield, which is at 0.1 divided by 0.1, which is actually 1, and then you multiply by 100, so you don't get any loss whatsoever. Okay, that's lossless. All right, you good with that, Ahmed? Because you put the 0.1, but I think that's what you meant. Yes. All right. Okay. Good. Right. Now, what we need to do is we need to figure out what's actually happening in reality. Okay. So 4.8. Now, the relative atomic mass of copper is 64. Okay. So 4.8 divided by 64 is 4.8 divided by, yeah, hold on a second. Yeah, 4.8 divided by 64. What's that? Can someone calculate that for me? .075. Thank you. Sorry. Okay, 0.075. Okay. All right. So what you're basically saying is that the reality is the real life situation is causing you to form 0.075 moles. Okay. All right. So your yield obtained in reality is 0.075, and your theoretical yield is 0.100, which is equal to 75 over 100. Okay. So your percentage yield is actually 75%, which is very generous for a chemical reaction. Okay. So your percentage yield in this situation is 75%. Now, there is a shortcut that you can actually take. If you move to slide 8, I think this is slide 8. Yeah, no, slide 9. If you move to slide 9, there is a slight shortcut that you can take, but there's your working out. That's the full working out in the, okay? I'm just conscious of time and I need to put in the last calculation, okay? Otherwise I'm going to run out of time.
Why do we have to calculate moles?
You don't have to calculate moles. That's actually a very good point. You don't have to calculate moles, but because this was the first ever example that you've ever seen, I wanted you to make sure that you actually made sense of this rather than just learn a calculation. Would that be fair enough to say? But you don't actually need to calculate moles. All right, you can just calculate the moles of zinc at the start. Then you do need to calculate the maximum amount of copper. So that's the Wonderland. But then what you could just work with is the maximum mass. All right, the maximum mass of copper that could be formed. You do need moles to try and figure out how much stuff you've actually made. And remember, 4.8 was actually given to us. Okay, so you do need to work out the maximum mass of copper. You've already got the number of moles of zinc. So if you use the equation, you know that 0.1 moles of copper could theoretically be made. Okay, would that be fair to say? Yeah. We're on slide 10 now, and we've got literally 2 minutes to fit this in. Okay, so what's this? Okay, right. Percentage purity. It's the final thing that we have to do. Okay, final thing. So percentage purity. Where are you? Here we go. So percentage purity is you're trying to figure out how pure your substance is. You get given a mass, and then what you have to do is you have to often work out the mass of the pure stuff that's in there, and then divide it by the mass of your whole sample. Okay, so let's say, for example, you've got an ore, a metal ore, and it's like copper, so there's valuable copper in there, but it's inside all of this other, all of this other unwanted rock. Okay, so you can actually work out the percentage purity of your copper ore. Okay, and that's the type of thing that they could do. In this question, they've actually I've left you with. You've got 7 grams of impure calcium carbonate. Okay, 2.5 grams of carbon dioxide reform. Calculate the percentage purity of the calcium carbonate. Okay, so basically, what you have to do is you have to work out the number of moles of your calcium carbonate. All right. And then you calculate the theoretical mass of the calcium carbonate used if pure. All right. So if you kind of have to look at it in a very similar way to what we did before. All right. You've got your theoretical one. You've got your actual sample. Okay. And then you've got your theoretical example. If this sample was taken the same size, if it was taken from Wonderland, okay? And then you can actually work it out using the Wonderland value, and then you have your mass of your pure sample, your mass of your impure sample, and you divide it and then multiply it by 100, and you should get the percentage impurity. Unfortunately, we are out of time now, but work your way through that, use your independent skills. If you are stuck on this, my direct emails are open, okay, so I can take you through that, but that's the end point of moles. Okay, there are a couple of people who did email me, but if you're heading towards core, remember that a lot of these factors will not be in your core spec. Some of these factors are already in the extended, but that's it. Okay. Right, okay, soon depends what my daughter's doing, Shane. Depends what she's up to. Okay, definitely in the holes. I'll stay around if you have a question about percentage purity, but it is the end of the lesson, so it's only fair for me to say you can go, but have a great restful holiday. Do get some rest, but do also start revising, okay? All right, bye Farah. Bye Mala.
Have a good day, sir.
Bye, sir.
You too, bye-bye. Bye-bye. Bye-bye.